Fluorescence. It describes a phenomenon where a molecular system absorbs radiant energy that emits light instantaneously in the form of radiation. That is, system absorbs radiant energy and this radiant energy is emitted in the form of radiation. This is known as fluorescence. It generally takes place at moderate temperature. Fluorescence can be stimulated by suitable exciting radiation in solid, liquid and gases. Generally, this fluorescent has the properties of liquid molecules. Okay. Next, the fluorescent emission ceases or stops as soon as the source of exciting radiation is removed. For this point, we have a question, that is, what happens when we block the source of energy? What happens when we block the source of energy? Consider a radiation or an energy. This arrow mark depicts a radiation or an energy, and this is a molecule, and this radiation is incident on a molecule. If we block the energy, that means a cross above this arrow mark depicts the blockage. Okay. If we block the energy or the radiation, the process of fluorescence stops. The process of fluorescence stops. It means that for the continuation of fluorescence, there is a continuous requirement of energy. Okay. Once this radiation or the energy is blocked, then the process of fluorescence stops. So the continuous requirement of energy is needed for the continuation of fluorescence. Okay. Next we have the two examples of fluorescence in visible light. They are first example, a solution of quinine sulfate emits bright blue fluorescent light. Second, an alcoholic solution of chlorophyll fluoresces with a deep red color. This emission of bright blue fluorescent light and a deep red color is only possible in a suitable exciting radiation. The condition for the examples of fluorescence to occur is that there must be a suitable exciting radiation. That means emitted light should be visible to our eye. Let's have a look. Examples of fluorescence occurs when the absorbed radiation is in the UV region of the spectrum and is invisible to human eye, while emitted light is in the visible region, which gives a fluorescent substance a distinct color that can be seen only when exposed to UV light. The condition for the examples of fluorescence to occur is that there must be a suitable exciting radiation. Okay. Next we have the energy level diagram of fluorescence. I have divided it into 5 steps. And the first step is that suppose a molecule is present in the ground state. Ground state means the ground state of a molecule is always a lower energy state. Ground state of a molecule always possesses a lower energy state. So it is a lower energy state. So it will always be a stable state. Okay. Ground state and the lower energy state of a molecule is always a stable state. And most importantly, they are generally singlets. So what is actually meant by singlet? Let's have a look. Molecule contain paired electrons. So these are the two paired electrons, and you know that electrons are negatively charged. Electron has a property to rotate around its own axis, and this electron is rotating in a clockwise direction and this electron is rotating in an anti-clockwise direction, and that the state of electrons in which both the electrons have opposite spin, then this state of electron is known as singlet state. Okay, this is a singlet state. Means here both electrons are paired in the opposite spin and they are parallel to each other. So these electrons are in the singlet state. Okay. In this diagram, here S denotes the singlet state, S0 is the singlet ground state, S1, S2, S3 are the higher singlet states. This is all about first step. Okay. Here S1 is the first electronic singlet state, S2 is the second electronic singlet state. Now the second step. In the second step, we are going to provide an energy to the molecule at the ground state, and the energy should be in the form of radiation. Okay, that is, in the first step, the molecule is in their ground state. In the second step, we are going to provide an energy. That energy should be in the form of radiation. Okay, in this diagram, that is, here violet color is the molecule and the orange color is the radiation or the external radiation which falls on it. Okay, this molecule will absorb this external radiation. This is what happening in the second step, absorption of radiation. Okay, and in the third step, next is the third step. After absorbing radiation or energy, molecules in their ground state is excited and leave their ground state and reaches to an excited state. Here, in the second step, the molecule absorbs the energy or the radiation or the wavelength of light. Okay, so in the third step, what happening is that after absorbing the radiation or the wavelength of the light, they are transitioned to higher electronic state, either to S2 or to S1. Okay, due to the absorption, an electronic transition takes place and the molecule transition to higher electronic state like its second electronic state S2 or first electronic state S1. Okay, and this excited state of a molecule is always a higher energy state. This higher energy means it would be unstable. Okay, so excited state and the higher energy state of a molecule is always an unstable state. And here is a note, that is, transition occur only for specific molecules and only if bombarded by a specific wavelength and energy is absorbed by the characteristic structure. The transition occur only for a specific molecule when the molecule which is bombarded by a specific wavelength and this energy is absorbed by the characteristic structure. Okay, that is, here the wavelength lambda 1. Here lambda 1 refers to the wavelength of light absorbed by the molecule to transition to the first electron singlet state, and it is excited to the first electron singlet state. Okay, that's all about third step. And in the fourth step, we know that there is a tendency for every molecule to be stable and they want to attain a stable state, or we can say they always want to maintain their stable state. So after absorption of energy, the molecule reaches excited state, but this excited state is an unstable state. So to attain stability, again molecule leave their excited state and start coming back to their ground state. Okay, here the molecule is in their first electronic singlet state and they remains for some time. And the time of fluorescence is about 10 to the power raised to minus 4 to the 10 to the power raised to minus 8. That is from 10 raised to minus 4 to 10 raised to minus 8. Okay, so after a short interval of time, the electron returns back to the ground singlet state, and in this transition, energy is released in the form of emission, and this phenomenon is called as fluorescence. And this is what happening in the last and final step, the fifth step. Okay, that means after a short interval of time, the electrons returns back to its ground state. They are returning back to their ground state by the emission of radiation. That means there is an instant emission of radiation. They only remains in the excited state for a short interval of time. That is in the fourth step. So after that, in the fifth step, they are returning to their ground state by the emission of radiation, and this emission is the instant emission, and this instant emission of radiation is known as the fluorescence. This is the last step. Okay. This transition involves less energy than the original absorption. The emitted wavelength is greater than the absorption wavelength. That means this energy and wavelength, they are in an inverse relationship. That is, higher the energy, lower the wavelength. Lower the energy, higher the wavelength. Okay, here you can see lambda 3 is greater than lambda 1. That is, the emitted wavelength is greater than the absorption wavelength. Okay, this emitted wavelength is greater than the absorption wavelength means in the emitted wavelength shorter the energy. That means here the emitted wavelength, higher is the wavelength. Okay, upon higher the wavelength, shorter is the energy. In the lambda 1, that is in the absorption wavelength, higher the energy, so shorter is the wavelength. So lambda 3 is greater than lambda 1. Okay, this is all about fluorescence. And this is a diagram. This is another diagram of the energy. And this is another energy level diagram of fluorescence. Here the straight arrows represent the radioactive transition. That means absorption of energy or radiation takes place and they are transitioned to the higher energy states. And these wavy arrows represent the known radioactive transitions. That is, known radioactive transition means that takes place without or either absorption or emission of radiation, and where environment acts as a heat for dissipation of extra energy as thermal energy. That means this is another diagram. That means same step takes place, I just given here. Okay, and this is all about fluorescence. I hope you understand. Thank you.